Okay, so this is a pre-lecture for experiment 1. Basically, it's about measurement. You must read the whole document, every word in the document. I'm just summarizing what I lectured with the rest. So I want you to pay attention to uncertainty for this experiment. Compare these two instruments. The top lap balance is approximately $300. The analytical balance is approximately $3,000. The reason being, this is more accurate. You see, it goes to the 10,000, this goes to the 1,000. Based on the uncertainties, you have 4 digits after the decimal point. So that's why this is expensive. So this 0 right here could be a 9, where this would have been, instead of 10, to be 0.9, or it could be a 1. That's what plus or minus means. This could be a 5 or a 6, depends on who is reading. So the last digit is always guessed. The rest are sure. So this is sure. This can dance around plus or minus 1. Okay. So the more the digits you have after a decimal point, the more accurate the instrument, the more expensive it's gonna be, because it has less uncertainty. You were to do measurements. Okay. You are to do measurements with glassware and check temperature for the boiling water. Now you look here, you see for 3 glasswares and a thermometer. So this is a burette. The burette reads from 0 going downwards all the way to 50, all the way to 50. So you read it from the top. Anyway, I want you to see that each of these lines, for example, from here to there, that's a 0.1, right? These are 0.1. From here to here is 0.1, 0.1, 0.1. So you do a tenth of 0.1, you get 0.01. So that gives you the uncertainty that's written here. From here to here is a 50. From here to here is a 50. Again, do a tenth of 50. You're gonna get plus or minus 5 uncertainty. The greater the uncertainty, the greater the error. So this flask here will give you more errors when you're measuring for volume of a liquid compared to the burette. This thermometer has calibrations with increments of 2. So if you do a tenth of 2, you get 0.2. That's why the uncertainty for this thermometer is 0.2. The one we have in the lab has increments of 1, so the uncertainty is 0.1. Alright, so if you have to get the measurement of a length of a ruler, for sure you're going from 9.1, 9.2, 9.3. So 9.3 is sure, and then we're going to guess it's 9.32. Now each of these calibrations is a 1. Let's see, is it a 1? No, it's a 0.1, because you're going 9.1, 0.2, 0.3. So it's 0.1. So you do a tenth of 0.1 for this ruler, you get 0.01. So the uncertainty will be given as 0.01. Now this means that this last guessed digit can be a 3 or can be a 1. And according to the manual, whoever wrote the manual read it as 9.33. So you still give plus or minus 0.01, because each of these calibrations is a millimeter. Okay, so the more calibrations you have, the more accurate the reading. Whenever you're reading a graduated cylinder, because this is called a graduated cylinder, you want to have your eye aligned with the bottom of the meniscus. So that this shape here is called a meniscus. So you read from the bottom of the meniscus, not at the walls, not at the edges. That's the goal. So if you zoom out this area, you're gonna see this. Is it zoom in or zoom out? Whatever it is, you'll see this. So each of these calibration is a 1. So this eye is looking at number 67. Now going back to the glassware itself, each increment it's a 2, right? Like right here is 48 to make this 50. So do a tenth of 2, you'll get 0.2. So because you have one digit after the decimal point in the uncertainty, the 67 should not just be written as 67, you have to write it as 67.0 plus or minus 0.2 for this one. But our graduated cylinder will have plus or minus 0.1. Anyway, you have one digit here, that's why I put one digit here and not just leaving it as 67. Okay, so uncertainties must be recorded. You can find the volume of regular shaped solids. For example, a sphere you'll use 4/3 pi r cubed. If you have a cube which has equal sides, then each side is an a, so it will be a times a times a. That gives you a cubed. If it's a cuboid, it will be a times b times c, for example, because the size will not be the same. For a cylinder, you'll have to find the radius. The radius is half the diameter. The radius is half the diameter. So use the r squared times pi in your calculator times the height, which happens to be the length. So height or length, you're gonna get the volume of a cylinder. So remember what we said, the uncertainty for the ruler, because you have each calibration as 0.1. If you do a 10 of 0.1, you're gonna get 0.01. So the uncertainty of the ruler is plus or minus 0.01. So here we're assuming the diameter is 2. So if you have this cylinder, we're assuming the diameter is 2.11, and we're assuming the length or the height is 3.56. So to find the volume, you're gonna divide the diameter by 2 to give you the radius, then you square it because the formula is pi r squared times height or the length. So you get this answer, but remember you have 3 significant figures in your division in the brackets. So you have to give yourself a reminder that this one has to be rounded down because the 4 is less than 5. So the answer is reported as 12.4 centimeter cube, but you are missing the uncertainty. So the uncertainty in this case, you need to take it as 0.2. This calculation that shows why it's 0.2, just for purposes of reporting it for this lab. Just know that the volume of an object, a small object, will have uncertainty of 0.2. Now what if it's irregular solid where you cannot use a ruler? What if it's a piece of rock or a piece of used chalk? How do you get the volume of such? So one would rather use displacement because the ruler will not help you, whereby you will take your graduated cylinder, okay, assume this is a graduated cylinder, blah 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 blah, and then drop your solid in there. Drop your solid in the graduated cylinder. So you read this volume and call it initial volume. Okay, that's the initial volume. After you drop the solid, the irregular solid that's shapeless, the volume increases because the solid displaces volume of equal to itself. So you read this volume right here, that will be the final volume. Okay, so the difference will be the volume of the object. So like in this case, the initial volume is 11, 12, we are guessing 12.4 plus minus 0.1 because each of this line is a 1. like we said, you just simply do a tenth of each of the calibration, you get 0.1. That's where this comes from and this comes from. So the final volume, if initial volume is 12.4, you drop the solid in the liquid in the graduated cylinder, the volume of the liquid goes up. So the final volume here is a 24 for sure, but it's somewhere above 0.5, so let's guess 24.7, and we're gonna give it 0.01 plus or minus because each of this line is a 1. Again, a tenth of 1 is 0.1. So subtract, you're gonna get the volume of the object by subtracting. So in this case it's 12.3. We're not reporting the uncertainty yet. There's math that determines that. That's why I told you to just go ahead and assume it's 0 plus or minus 0.2. Okay, so that's another measurement you do in this lab, you would have done in this lab, or you will do in this lab. Okay, just to classify physical properties, you know, there are properties, the physical properties that change in value if you have more of the sample. So for example, if you have 1 spoon of sugar, if you drop it on a weighing balance and record the mass of the sugar and then take it out and then drop it on the same weighing balance, drop 2 spoons of sugar. The 2 spoons of sugar will weigh more than the 1 spoon of sugar, which means mass is affected by how much the sample you have. And in fact, the more liquid you have, the more space it occupies. The more solid you have, the more space it occupies. So volume is also affected by how much you have. It changes with how much you have. Such properties that change in measurement based on how much they are called extensive properties. They are affected by the amount of the sample. Intensive properties are not affected by the amount of sample. For example, boiling point. The boiling point of 1 drop of water and 1 gallon of water is always 100 degrees Celsius. Okay. Also density. The density of 1 drop of water is roughly 1 gram per centimeter cube. The density of 1 gallon of water is again 1 gram per centimeter cubed. Density does not change, boiling point does not change with amount. Part of this experiment requires that you do density measurement, and also experiment 2 will have you do lots of density measurement. Okay. Keep in mind significant figures. So the other thing you needed to do is, or you need to do in this lab, is to use a Bunsen burner. You have a wheel down here that lets the gas pass through the Bunsen burner. Okay, it's like this valve is like it's like a gate for the gas. If you close it, no gas will come in through the burner. It's gonna come, but it's gonna be blocked from going up the tower, the barrel. Okay, so before you light up the Bunsen burner, you want this closed, and then you open it slowly as you attempt to light it up. Then up here, this sheave is an air inlet. You need oxygen to burn up your organic gas. So this could be a methane, or it could be propane. This is a chemical formula for propane. You see you have carbons in there. You'll need oxygen to burn up these organic molecules, whether it's methane or propane, the natural gas. You'll need oxygen. So the more oxygen you get, the more carbons will be burnt from the formula, the more heat you get. If you limit the amount of oxygen, some of the carbons will be incompletely burnt, and that's why you'll see the glow, what you guys see as a yellow flame. So the yellow flame implies there's not enough oxygen to burn all the carbons. Okay, for the blue flame, you have enough oxygen, so all carbons are burnt up. So that's why the blue flame is hotter than the yellow flame, because all carbons are burnt up. In fact, this is not as bright. Sometimes you might think the flame is not there, but it's really there. So you want to be careful not to poke your finger up there to check if the flame is there. You're just gonna scream. So this is called non-luminous because there is no bright, glowing, and burnt carbons. This is called luminous because it's bright. These glowing and burnt carbons, and of course there's all those other parts of the flame. Okay, so this is just precautions. We always go for safety. This glassware has got a pipette. It's called a volumetric pipette. Okay, this glassware is volumetric pipette. It's you needed to use it also in the lab. You simply put a pump up here, a pipette pump up here with a wheel that will take in the liquid. You don't want to use your mouth. So if you take in the liquid to this point, the volume of the liquid going down will be 10 ml. You have 20 ml pipette, you have 25 ml pipette, you have 50 ml, or you have 40 ml, you have 50 ml. So for this experiment and experiment 2, we used or will be using 20 ml. And next is just the experimental setup. So one more thing I want to mention is there's another thermometer called a digital thermometer. Okay, so this is the digital thermometer, meaning it has a metal here that if you put it inside a boiling liquid, then it's gonna give you the temperature here. So you'll get the temperature here displayed on your display. Okay, of course you know the regular glass thermometer. Okay, with a bulb. Again, you dip that in there to check the temperature of boiling water using your Bunsen burner as a source of heat. So for this experiment, one wanted to know whether the digital thermometer is better than the glass thermometer. You want to know which one is more accurate. Okay, remember metal is a good conductor of heat than glass, but let the experiment decide. Okay, so for this one, you're measuring volumes with a graduated cylinder. Okay, this one you're trying to find the density using mass over volume. I mean, you can read all this text and just see what the procedure says. So that was for experiment 1. I'll find a link of what was done during experiment 1. Okay, and this is the data table. You have a copy of this data table on Moodle, but this data table must come with your report sheets. Remember, you have to fill up the uncertainties. You have to fill up the uncertainties for all these tables. The flask is taken to be exact, so no uncertainties. And in fact, I would say this says error, so don't fill up that point because errors are different from uncertainties. Okay, so you read the procedure, you'll know what needs to go in here. So I'll just provide the numbers, and then you read the procedures for each of these parts, and then it's gonna make a lot of sense because I'm just trying to go over the manual, but the actual experimental procedures, you have to read them and then apply the numbers and then answer this report sheet. Okay.